the apple with the fall of the moon around the Earth. So that's Isaac Newton, and that's what I'm going to be talking about, mathematical pebbles, in the next couple of lectures. Now, when one presents a lecture on mathematics, it's very possible to lose one's class around about 2/3 of the way through the lecture, especially if mathematics is because it's all built like that. So the psychologists tell us that if you draw a graph of the concentration level measured over here against time, then it will go something like that. But if you take a break in the middle of the lecture, for whatever reason, at this stage, the concentration level when you start again will be higher, and it will descend, but it won't ever get down as low as before. So I've made it a principle in undergraduate lectures to always stop in the middle of the lecture, often to do a little bit of housekeeping, like the next test is on such and such a date, or don't forget the marks are up, or this homework is due, or whatever. Now, there may not be housekeeping, but if I don't have anything of a housekeeping nature, they'll tell an anecdote or something like that. And I've got a reputation for doing this sort of thing. I think it's a very valid educational thing to do in the middle of the lecture for that reason. But having been lecturers for a long time, I'm often met by somebody in the street who says, you lectured maths to me in 1984. To which I reply, well, yes, well, I'm afraid I don't remember you. Yes, I remember that you lectured us. I don't remember any of the mathematics. But I do remember that you told jokes during the lecture. But I don't remember the jokes either. So that's what I'm doing in this series of lectures. All those little mathematical pebbles I'm going to do with maybe venturing into the oceans of truth between the pebbles. So let's start with numbers as symbols. Now, I'm sure a lot of you play Sudoku, which when it came out was billed by the newspapers as being a game about numbers which doesn't require any mathematics. I think they said that in order to make people comfortable. It's wrong on both scores. Sudoku is not a game about numbers. It's a game about 9 different symbols. So you could play Sudoku with those symbols, which would be very annoying. Now, those are the symbols that appear above the digits from 1 to 9 on the keyboard. But imagine playing Sudoku with those symbols. And secondly, Sudoku embodies a whole lot of mathematics and combinatorics and possibilities and logics and all sorts of different mathematical thinking. So let's think of numbers as symbols. They come with a built-in ranking, 1, 2, 3, etc. And as such, they're often used in that respect. And in no other, such as numbering the houses on a street. Although sometimes they put the even numbers on one side and the odd numbers on the other. So you have to distinguish between the two, unless you're in Downing Street, which is famous for having number 11 next door to number 10. And then, of course, streets are also named sometimes alphabetically in terms of trees, ash, beech, cedar, and so on. Librarians, of course, use the number symbols and the alphabet as in both to categorize and shelve their books. So, but numbers, when you start to use them as numbers, need symbols. And here are the symbols that the Egyptians used 4,000 years ago, hieroglyphic symbols. So you had the numbers from 1 just a vertical stroke, 10 a heel bone, 1,000,000 is a man in astonishment at such a large number. And if you wanted to make numbers, you just strung them together. It didn't have to be in any order, you just strung numbers together. So if you have those numbers as symbols, that works very well. The Greeks and the Hebrews used their alphabets for numbers. So here you have the alphabets, the Greek alphabet and the Hebrew alphabet, which are very closely related, probably because they came from a Phoenician origin. But the Greeks would use the alphabet, alpha, beta, gamma, delta, those letters to represent the numbers 1, 2, 3, 4. So you had a built-in order of the alphabet. And the Hebrew alphabet, Aleph, Beth, Gimel, etc. That's fine. And what you do there, again, is string the numbers together, and there are other little variations that you use. But then you run out of numbers. You see, when you passed 1,000, now you need to invent more symbols, and it gets more complicated that way. Well, the Romans used a system which everybody thinks is alphabetical, but it's actually not. The Romans used symbol, the vertical line for 1. The V was half of a 10, and the X for 10 doesn't stand for any Latin letter, it's just the symbol. Then you have C for 100, well, happens to be the same letter as the beginning of centum for 100 in Latin. A D for 500, and everybody would think that they use an M for 1,000,000, for 1,000 at least, which is not true. The Romans did not use M. That was a medieval or much later use. The Romans used a symbol which looked like a sideways 8 almost, and half of that symbol was a D, which is what they used for 500. So just to demonstrate what the Romans did, here is a Roman pocket calculator for anybody who had a pocket in their togas. It's made of metal, about the size of a little bar of chocolate, and here you see the symbols. One that's a bit obscure, but that's 10, 100. That's the symbol for 1,000. And then 10,000, and then 10,000, 100,000, and 1,000,000. Quite a good system. And by the way, the Romans also worked with fractions, and these little beads sliding up and down on the abacus are used for fractions, mainly twelfths. So that's the Roman system, which was actually quite effective. But these systems all had the disadvantage that you had to introduce more and more symbols the larger the numbers you got. Now, over in the Americas, the Mayan civilization in what is now Mexico had a symbol of dots and lines, and that's how they that 1, 2, 3, 4, 5. So it was 5 based in a sense, but also 20 based. So when you got to 20, you started with the dot again. But their major innovation was to have a 0, because if you're going to string together a lot of these symbols, and you want to say 105, then you have a symbol for 100, but no 10s and the 5. And the Mayans had that symbol for 0. So that 20 that's how they'd write 20. They're reusing the dot, but that indicates that it's a dot shifted over one to the left. Of course, what we do is use our zero symbol, but I'll get to that in a moment. But that was developed totally independently and had no effect on the development of numbers and mathematics in the Western world. The Mayans also had a god associated with each number. So they had those symbols as well. But these were inscribed on monuments. I mean, you can't do calculations with that stuff. I mean, the one point about number symbols is that they've got to be instantly recognizable and distinguishable quickly from other symbols. And we'll get back to that point. So that was the Mayans. But going back to the Middle East and going back to 2000 BC, we get to the mathematicians of ancient Babylon who had a number system which fortunately has been marvelously preserved for us because they used clay tablets. And clay tablets, when baked in the sun and then get lost in the sand, are preserved, and thousands of years later you can dig up a clay tablet like that and you look at it and you say, 1, 2, 3, 4, 5, 6. These are cuneiform letters, wedge-shaped letters, engraved on a wet clay, either with one end of your stick which gives the vertical, or the other end of your stick which gives the going up 9, 10, then 10 and 1 is 11, 12, 13, 14. That's their system. Well, that's clear enough, but what's happening on the right-hand side is that we've got 9, and then that's 10 and 8, which is 18. The next one is 2 10s and a 7, 27, 36, 45, 54. It's obviously a 9 times table, and it was discovered in what turned out to be a schoolroom 4,000 years ago. And but now just get on here. 9 6s are 54, 9 7s are 3. That means 60 with a space. And they used a base 60 system. And so it goes on from there to 9 8s are 63, 6 and 10 and 2, 72, 81, and so on, until you get to 9 14s, 126. Well, there's the other side of the same tablet. It just goes on. But you can see how that gets very jumbled. They're not easy numbers to recognize. Well, it may be that some inexperienced school kid 4,000 years ago was responsible for making that tablet, but you can read the numbers off it quite easily. Here, more systematically, are the numbers up to 50. But the point about these numbers is, if you looked at that one and that one, without my having told you that that's 49 and 58, you would actually have difficulty you'd have difficulty in distinguishing between 49 and 58 just by looking at them. And the point about our number system is that the symbols we use are recognizably easy to assimilate and easy to distinguish. So our system, using just 9 digits and a 0 system, comes from India originally and is often referred to as the Hindu-Arabic system. That doesn't actually give credit to an important transmission through Persian culture. Persians not being Arabs, of course. But they wrote in Arabic. That's why these things are just called Hindu-Arabic numbers. One of the great mathematicians of that time is far better known to us through his poetry, namely Omar Khayyam. He was a very important mathematician of old Persia. But what the Hindu system introduced, which was just most important, was this document. It dates from about 300, 400 AD, and it's got various numbers on in early forms. I don't know what it all means, but this one over here, that's a 0 as a placeholder. So as a placeholder, the 0 was introduced to separate the numbers on either side. And that's the Bakhshali manuscript discovered in what is now Pakistan. And the placeholder, the dot, became used in the Western world, and it morphed into a 0. Or we often say O, but it's got nothing to do with the letter O of our alphabet. But the point is that the Hindu-Arabic system had just these 9 symbols, plus the 0 is 10, and could represent any number as long as you used the place value system. And that's what we use today. And it's very effective in recording numbers and also in doing calculations. So let's talk a bit about the numbers. The 0, first of all. The English regard the number system, which we call the natural numbers, as beginning with 1, 1, 2, 3. The French, for some reason, regard natural numbers as beginning with 0. The concept of 0 as a number is not the same as the concept of the symbol 0 used in number systems. 0 as a number used in arithmetic was discussed by the Indian mathematician Brahmagupta in about 700 AD. And he was the first to discuss 0 as a number in algebra and arithmetic, including the danger of division by 0, which I won't go into at this stage. We call the 0 is an Arabic word, or comes from an Arabic word, which means like cipher, which means something of no consequence. We use the word naught, spelt either with an A, as in naught for your comfort, or something comes to naught, or naught, which often means 0. And strangely enough, the word ought is also used. That may have come about because an ought could become a naught in English, spoken English. And the ought there comes up in this quote, which I rather like, as a basic principle of economics. Annual expenditure, annual income £20, annual expenditure 19, 19 and 6 result happiness. Annual income £20, annual expenditure £20 ought and 6 result misery. Mr. Micawber, Dickens, David Copperfield, although Mr. Micawber was absolutely hopeless at economics, as we know from the stories. Let's say something about, I guess it's 57 years since we moved away from pounds, shillings and pence, but I hope I don't have to explain what those things mean to this particular audience. Now, number 1, it's interesting that in some languages, typically French and German, 1 in French and ein in German is the same as the indefinite article. So that's the number 1. 2 in English, we have the word two, of course, and the archaic twain, now encountered mainly poetically or biblically. Twain massy keys he bore of metal, twain massy keys a bore of metal twain. two massy keys he bore of metals twain. Twain were casting dice from the ancient mariner. Kipling's east is east and west is west, and never the twain shall meet. Biblical, each with twain, each one had 6 wings. This figure in Isaiah. With twain he covered his face, with twain he covered his feet, and with twain he did fly. This, of course, from the King James Version. And Mark Twain, by the Mark Twain, was a call by the river pilots on the Mississippi, and Mark Twain took his pseudonym from that call. So the word twain is an Old English word, and then I noticed that my printer at home is HP LaserJet M1130 MFP Twain. Why, I'm not sure. The point is that twain is Anglo-Saxon, and the interesting thing is that twain is the masculine form of the word, and two is the feminine in Anglo-Saxon. Well, two-ness is a special kind of plurality. In English, we have a distinction, for example, between the word both, which means two, and all, which will mean more than two. And two has a special treatment in some inflected languages. So Russian takes the genitive singular for 2, 3, or 4. So you say 2 of horse, 3 of child, 4 of ruble, while 5 takes the genitive plural. So the lower numbers are considered to be more singular than the others. And in English, of course, we have a number of words which are of plural form, which are singular, because of their inherent two-ness, like trousers or glasses or compasses, lights, tights, scissors, pliers, secateurs. There are also special words for two in English, especially in English hunting parlance, which speaks perhaps of a very primitive origin. A brace of partridges, a couple of hounds. Right, on to 3. 3 in South Africa, in South African currency pre-1961, as I was saying, 3 pennies, threepence in English, or threepence, was a South African coin which was nicknamed a tikkie. That word was eliminated, as the coin was, at a stroke on St. Valentine's Day in 1961 by decimalisation. The origin of the word tikkie is obscure. It may be Malay in origin. It's not really known, but some say it might have come from an English slang word for sixpence, namely a tizzy. Well, I wanted to put this picture up of a very well-known maths teacher, Takeda Yaga, who bore a striking resemblance to a famous clown of Boswell's circus, whose name was Tikkie. And Tikkie was a really brilliant maths teacher, and here he is, sketched by a member of his class not paying too much attention to his maths, who was sitting in the front row. He sketched it on the inside cover of his textbook, which bore the official departmental stamp. Ron Bosch Boys High, the name known today, Zapiro. And that's such a lovely cartoon. For anybody who knew Tikkie, you just recognize that immediately. 1976. Now, most cultures and languages count in 10 because we have 10 fingers. However, there are variations, typically giving a special place to 20 because you could use your toes as well. And English, we interestingly, they only start using compound numbers after 10 from 13, 14. We have special numbers for 11 to 12. We don't say 1 teen, 2 teen. And the French do the same. and so does German, and Afrikaans, of course. It's been suggested that this base 12 idea comes from the fact not that we've got 10 fingers, but that we've got 12 knuckles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can do calculations if you work on the idea using the base 12 on your fingers. And this, of course, uses a distinctly human trait that apes do not possess, namely the opposable thumb. So chimps would not be able to count like that, even though they have 12 knuckles. So some languages have special words for 11 and 12, as I mentioned, French, German, Afrikaans. Unlike English, Russian starts the compound number words at 11, which means 2 on 10. 12, which means 2 on 12, 2 on 10, which is 12. And interestingly enough, when they say 12, they are using the feminine form of 2 in the Russian language. By the way, it occurs to me that in English, our teenagers are those that are 13 or older. I've never been able to work out what happens in other languages. I looked up teenager in a French dictionary, didn't find a word for teenager except an explanation that it was children over the age of 12. The French goes 11, 12, 13, etc. Then it becomes logical after they get to 20, but then French becomes totally illogical again when they get after 60, because 70 is 60, 10, and 19 and 80 is 80, which means 4 20s. But that's how they seem to manage. Another word in English for 20 is score, as in the biblical, the days of thy years are 70. The word is often misused by journalists. Have you ever noticed? They will say, scores of people flocked to the beaches on Boxing Day. They don't mean, 20 or 40. Score is 20. In Latin, 20 was viginti, and curiously, 19 was unde viginti, 1 less than 20. But then the Romans had this curious system of counting. The Ides of March would be on the 15th, and then the day before would be called the day before the Ides of March. So 1 day, 2 days, 3 days, 4 days before the Ides of March. The calendar was complicated that way. Italian has an anomaly which I could never work out. In Italian, the quattrocento, which is what the art people use, means 400. But they don't mean 400, they mean 1400, namely 15th century. American counting is a little different from English. We say 102 and they say 102. And since 9/11, we know that their calendar numbering is back to front, namely month, day, year, where we go day, month, year. Here's a numbering system that I really like. It comes, if you want to get to sleep and count sheep, this is the numbering system you should use because it was used by shepherds in Cumbria, the north of England. Yan, Tan, Tethera, Methera, Pimp. Sethera, Lethera, Hovera, Dovera, Dick. It's interesting, the etymologists can have great fun with this because the word for 5, Pimp, is etymologically connected with fünf or 5 even in the German, whereas Dick seems to be related to Decem, 10. But let's look at the Hovera, Dovera, Dick, 8, 9, 10. In another dialect, that would be hickory, dickory, dock. The mouse ran up the clock. The clock struck 1, the mouse came down, hickory, dickory, dock. Nice little poem, which I believe is the first limerick when you think of it. But while I'm talking about nursery rhymes, here's something not quite relevant. Another nursery rhyme that's got a hidden mathematical and numerical context is Little Miss Muffet. Here she is in a famous painting by Millet, sat on a tuffet, eating her curds and whey. And she's sitting here, it's not really distinctly drawn, a tuffet here, sort of a mound of grass. And that's what is often referred to in OP's, the famous OP dictionary of children's nursery rhymes. They say a tuffet was a tuft of grass. Well, it wasn't actually. If you look up old uses of English, a tuffet was a 4-gallon container, which is just sort of the right thing for sitting on. But let's get back to that Cumbrian numbering system, because it goes on from there to Dick. Whoops, wrong way. Yanadic, Tetheridic, Metheridic, Bumfit. Or they might say in North Cumbrian, Bumfit. How many members of a Cumbrian rugby team are there? Bumfit, Pagum. And then they go on, Yana, but 15 is a unit, and they carry on from there until they get to gigot. Wonderful words, all, of course, of Celtic origin. So the days of thy years are, in Cumbrian, Tetherigigots and Dick, which goes rather well. Now, there are other numbering systems in the Celtic languages, and Welsh is one. It has two numbering systems. The old numbering system was vigesimal in character counting in base 20 and got complicated. There's a new number system which is decimal and much simpler. That's 99 in the old Welsh system. It's actually where are we? 4 and 15 and 4 20s. 4 and 15, rather like Bumfit in Cumbrian, Celtic of course, and 4 20s and 4 20, 99. But that's not the way to count, really. It's just too complicated. What is of interest, I think, is that Celtic numbering systems must have been all over England. The Roman invasion didn't seem to have any effect on that. But what did have an effect was the other colonizers, namely the Anglo-Saxon, because all the numbering words in English are Anglo-Saxon in origin. And the first time you meet a number word that's not Anglo-Saxon in origin is 1,000,000, namely a big 1,000. All the other words up to that stage are Anglo-Saxon. But there is one exception which is interesting, and that's not in the numbers which we call cardinal numbers, but in the ordinal numbers. First, second, third, fourth, fifth. Second is Latin in origin. First, third, fourth, fifth, sixth, seventh, etc. are all Anglo-Saxon in origin. Now, second seemed to have overtaken the Anglo-Saxon word. The Anglo-Saxon word for second is still in use. It's in use today. It's other. So we say on the other hand, on the one hand, on the other hand. Or we say the other woman. Or we say every other day, which means every second day. So, but of all languages with counting words, Asian languages such as Chinese are most efficient. Here are the Chinese words for, I'm not going to try to pronounce them, sorry, because They have all sorts of intonations and things like that. But there you have 1, 2, 3, 4, 5, 6, 7, 8, 9, all single-syllable words, and all quite distinguishable in sound. And then you have the multipliers 10, 100, 1,000, and 10,000. So 9247 becomes 9 times 10,000, 2 times 1,000, 5 times 100, 4 times 10, and key is 7. And that's a very efficient and easily learnable system, and you string numbers together like that. There is good evidence, and child psychologists have looked into this in some detail, that Chinese children learn their words more quickly than English children of the same age, because they just need 13 words, while in English children need 29 words for the same range of numbers. When you think of 13, 14, 15 not being 3, 10, 4, 10, 5, 10, then of course we have the irritating thing that in English 13 is easily confused with 30 if you're speaking rapidly, 40, 50. And I remember working in Old Mutual as a student, when we were checking numbers with each other, you always said forti and fifti to make sure that you weren't confusing that with 14 and 15. So English is not all that efficient in that respect. Germanic languages, including Afrikaans, have this curiosity of inverting the order, so they still say 4 and 20, whereas in English that just remains in the number of blackbirds baked in a pie. Some years ago, somebody did research in Afrikaans children's comprehension of numbers, and they found that this was a difficulty in Afrikaans. I guess on the whole, kids get through it fairly quickly. Now at this stage, I'm getting out of my depth with the use of languages in early learning of mathematics. But I know very little about counting, for example, in African languages, and I believe it's complicated. Perhaps that is why the cricket commentary in African language is often given in English. The scores are given in English because the numbers are complicated. Then, because there's cricket on at present, I found this in my record. Now let's read this one carefully. Umla has now scored as many runs in this innings as he has scored in his entire career if you subtract all the runs he'd scored in his career before starting this innings. How true that is. Now, but getting back to this numbering system in African languages, and here I really can't offer anything, but surely there's something serious here when right at the start of teaching mathematics in English to a black child, they have to relearn how to count in English from their complicated system in their particular home language. Now, numbers. It's about time I really got onto the subject of my talk, namely 666 and all that, which of course has, with acknowledgement to Sellers and Yetman's famous book of history. But in the Bible, you can find lots of references to numbers. So let's have a look at the book of Genesis, which is full of this sort of thing. Whoops, no, not that one. Genesis. Enoch lived 65 years and begat Methuselah, and Enoch walked with, etc. All these very detailed numeration systems given setting out the generations of Enoch, Methuselah, Lamech, and Noah. Methuselah was Lamech's father and Noah's grandfather. And if you work out those numbers, and as I say, Methuselah lived to 969 years and he died. Well, and if you work out the numbers in which he died, it turns out that Methuselah died in the year of the flood. Lamech had died earlier, his father. So why was Methuselah not taken into the ark? Well, it's suggested, it may be because Methuselah was rather getting on a bit. His wife's not mentioned, so he was beyond childbearing age, and after all, the residents in the ark had to reconstruct all our, rebuild our civilizations. So he wasn't taken into the ark. There were 8 on the ark: Noah, his 3 sons, Shem, Ham, and Japheth, and their wives, and Noah's wife, all of whom are not named. Now, 8 in that tradition signifies new life, resurrection, and new creation. The 8 came out of the ark, and Granddad didn't have a place in this theory, so unfortunately, ancient tragedies seem to have died in the flood. Now, in both Hebrew and Greek, as you might remember from the slide that I showed a little while ago, they used letters to represent numbers. So every word can be given a numerical interpretation simply by adding up the numbers that the respective letters represent. And this sort of numerology is practiced by certainly scholars, biblical scholars of the Old Testament. It's called gematria, and there's an enormous literature on this subject. And in certain Christian churches, it's called Bible numerics. So a little bit about Bible numerics, although this one is far not really serious. Psalm 46. That's from an ancient Psalter, I guess. If you take Psalm 46 and you count the words of the psalm from the beginning, the 46th word is shake. And if you count the words of the psalm from the end, the 46th word is spear. Shakespeare, therefore, had a hand in the Bible. I thought this was a great joke, but it does seem that there are people who really take this seriously. Now, of course, Shakespeare was the premier wordsmith of his day, so he could well have been consulted. No, he couldn't. He was a playwright, lower order. The translators of the Bible, the King James Version that is, were serious clerics and scholars of Hebrew and Greek. Shakespeare would not have been on that list. But it's a lovely story, and it's worth repeating, even though it's not true. Well, then we get on, of course, 666. And here we have in the book of Revelation, and he causeth all, both small and great, rich and poor, free and bond, to receive a mark in their right hand or on their forehead, and that no man might buy or sell, save he had that mark, or the name of the beast, or the number of the beast. Here is wisdom. Let him that hath understanding count the number of the beast, for it is the number of a man, and his number 666. Book of Revelation, chapter 13. Now here's a lovely question. I'm sure you can catch people out on this one. It's the sort of question that occurs on that program QI. How many numbers are there in the Bible? Well, there's a whole book of numbers. And numbers are mentioned frequently, as we saw with the Methuselah story. How many numbers are in the Bible? New Testament and Old Testament put together. 1. There's only one number in the Bible. And that is, in this context, it's the only case in the Bible where the number is written numerically, as in Greek, this case, 666. All the other words, number words, are written out in the Bible, in Hebrew or in Greek. So they are number words, I'm being pedantic here, as opposed to the number 666. It's the only number in the Bible. Well, it's led, of course, from that context to a great deal of superstition, and people are scared of that number and avoid it out of an irrational fear, which has that name, or a sort of phobia. Well, of course, that just means fear of the number 666. And a couple who were Ronald Reagan and his wife Nancy, when they moved out of the White House after his term as president, took a house and they discovered that the house was in Bel Air and was number 666 St. Cloud Road. They changed the number to 668. Incidentally, for those who would be opposed to Reagan, Reagan's name was full Ronald Wilson Reagan. 6 letters, 6 letters, 6 letters. And we should also note that the World Wide Web is abbreviated to www. etc., etc., etc. In the W, it doesn't exist in the Hebrew alphabet, but in Hebrew it would be written with the 6th letter of the alphabet, Vav. Vav is number 6, and 6, 6, 6, Vav, Vav, Vav in Hebrew is www, 666. That's all very worrying. However, it turns out that a fragment of papyrus was discovered and revealed and investigated closely in 2005. Oh, I want to say something about this first. These are barcodes, of course. There was something else that when these barcodes were introduced, people were very worried about them because they said these vertical lines here, there, and there, and there, those 3 sets of vertical lines, which occur on all barcodes, are 666. And people, there was a big movement about this was about 25 years ago, a big protest about this. Actually, they were quite wrong in that those 3 sets of lines were used for the scanner to sort of adjust itself, because the scanner goes across the barcode in all sorts of different direction, and it calibrates itself on those 3 sets of lines. And the numbers themselves are not coded in that sort of naive, simple way. The numbers are coded in a far more complicated way. So let's see. Here you see 2 vertical lines, but that's not a 6. And here again, that's not a 6, it's a 3. And there it's a 0. So the story that this barcodes, the number of the beast on all the products you were using, was biblically forbidden, was promoted, but to no effect. We've got barcodes with us now. However, it was discovered that maybe everybody was wrong. here is a papyrus, a fragment of a papyrus, which is the earliest fragment of papyrus known, and it's identified as being a fragment of the papyrus of the Book of Revelation. And it happens to be that this piece, there are more fragments in the collection in, I think, Oxford University. There are more fragments there, but this particular one has got the number of the beast on it. And here it is. Whoops. Sorry. There it is. Chi, the Greek letter meaning 600, and that's the letter Sun P, which is an archaic Greek letter for 6, but in the middle, that's iota, which is 10. So, in that fragment of the papyrus of the Book of Revelation, the number was 616, not 66, not 666. So the 666 could well be just a misunderstanding or a transcription error somehow or other. There have been various attempts at interpreting what 666 could mean. It's popularly said that it's Nero. Well, you've got two options. You could either use the Latin form of the name Nero or the Greek form Neron and use the counting system to add up to 666. And Nero, of course, was pretty nasty to Christians, so it's a good guess that he was regarded as beastly. However, many scholars say that the numbers can't represent Nero. But in either case, it looks like 666 as a number has got actually an undeserved reputation. 50 less 616 should be the number to worry about, but nobody does. And so on that, I think it's time to stop. Thank you. There's time for questions if anybody has them, but
the Celtic numbering system, those words, are they related to types of sheep?
I don't know, to be quite honest. I don't think so.
They might be names of different breeds of sheep.
Well, I think the Celtic number systems, which you also find the words in Scotland and in Wales, and maybe so you get. I think there were. I've never seen any description of that as referring to the types of sheep. Yeah, sorry. Yeah.
There's a film tomorrow, also with the title Mathematical Pebbles. Have you seen it?
Oh, no, I haven't. I don't know what those movies are. I don't even know whether they just used my title, Mathematical Pebbles, and have put in a couple of things that they found somewhere. So tomorrow morning, there are 3 or 4 movies being shown, and under the heading of Mathematical Pebbles. I wasn't consulted even. I just discovered this the other day. But I'm sure they're going to be nice because they've got a very canny team collecting and checking the movies that they show. Yeah, yeah.
Those Chinese numbers, it looked to me as though they could be put on the abacus. Does it have a different...
A question about Chinese numbers and the abacus. You can say quite a lot about the abacus. The Chinese abacus looks a little bit like the Roman abacus that I showed here. There's also Japanese abacus. And here's something that's actually very interesting. In Japan, they don't allow calculators in school. Finished. They do have an abacus. And they have abacus contests where they get the kids together and they give these numbers to add up as fast as they can. And it's hugely popular, even spectator sport. You see these numbers going up on the screen, and the children have to add them. And you get these abacus champions. They get so good at doing abacus calculations that they can do it without an abacus. Namely, they visualize the numbers on an abacus. So these numbers are flashed up on a screen like that. A dozen numbers in 5 seconds. And they can visualize the numbers on the abacus being added up. And you see them thinking about it, and their fingers are working. And they come to the total. They can give the total in as quickly as that. When asked afterwards, the total is correct. When asked afterwards, what were the numbers? No idea. Nor have they any idea of the subtotals that must have gone on. But they are just visualizing the beads on an abacus sliding up and down, and they see the answer. So the actual calculation, there's no calculation taking place. They're using a different part of their brain from our calculating brain, which is apparently up there. But they're using fingers. So it might be like something like coming visually, like notes on the piano, to your fingers without having to go through an analysis in the brain. But it's interesting that your brain up there is the same part of the brain that controls your fingers. It's a huge part of the brain that controls fingers. So it's fascinating how much is being investigated by neuropsychologists on numbers in the brain and how they are manipulated and how brain-damaged people can handle numbers but they can't handle words or something like that. But this is a whole different area. But there's a book that I referred to in the summer school blurb called The Number Sense, which is really very well worth reading.
I wonder how many people are aware of the fact that there's no such thing as uninteresting numbers.
Yes. You mean uninteresting whole numbers?
Uninteresting whole numbers.
There's no such thing as an uninteresting whole number. Well, because?
If you could divide numbers into interesting numbers and uninteresting numbers, then if that could be a lowest uninteresting number.
There would be a lowest uninteresting number, which by definition would be interesting. By the way, you were talking about positive numbers also, and you mean whole numbers. You see, that argument doesn't work with fractions. Because if you had a list of fractions, there might not be a lowest fraction. If you take all the fractions bigger than pi, there's no lowest one. Sorry? Okay. Thanks very much. Stephen, do you want?
How do you translate numbers into binary computing?
Yes. Well, you successively divide them by 2. There's a topic for another 5 minutes of lectures. There's a system called Russian peasant multiplication, where you take your 2 numbers, you double them on one side, and you halve them on the other, and then you scratch out the numbers where you had to leave a remainder, and you add up, and you get the sum, the total. So this is a system of multiplying any 2 numbers without knowing how to do your general tables, only knowing tables of multiplying by 2, dividing by 2. And it's called Russian peasant multiplication because, in fact, it is known, or was known, among Russian peasants. And what's actually happening there is that the division by 2 is effectively reducing one of them to its binary representation, and the bits that you need that aren't crossed out, probably this explanation is not very good, it needs more time. But that is how you convert to binary. And it's a very easy little thing to do on a computer, which of course the computer does all the time because the computer works on off, and everything's in binary.